All right, so we've been doing rotational motion, uh, and I believe that we last time had established the idea that there's an equivalence between uh, like linear variables from chapter 2 and the rotational variables from chapter 10 when it came to kinematics, and we learned how to do the description of an object that's rotating. We introduced the idea of angular acceleration or angular velocity and angular position, all of those things. But where we're going to go next is we're going to extend that even further, because after chapters 2 and 3, when we finished up kinematics, we switched gears and started talking about dynamics. And dynamics is the other branch of mechanics where we start to care about not just how something is moving, but why it's moving that way. And everything we've done up until this point is going to have a rotational analog. And we're going to establish what that analog is today. Now, we already know part of it from chapter 9, because chapter 9 introduced the concept of torque. And torque is just the rotational analog of a force. Switch to the camera. So, again, we're going to keep our sort of translational motion. And the rotational equivalent kind of split down the middle categorization. And we know that in translational motion, objects can be subject to forces, forces that we measure in newtons. And a force causes an object to accelerate. In chapter 9, we learned about the concept of torque, given by the Greek letter tau. Torque was defined as R cross F and therefore has units of newtons times meters, right? So torque is the angular equivalent of a force. And in chapter 9, we solved problems where all the torques on an object ended up adding up to 0, and therefore the object didn't move. But what we don't know is what's going to happen if the torques don't add up to 0. We haven't figured that part out yet. We know the translational version of that because that was chapter 4. We learned that if you add up all the forces, the sum of the forces equals ma. That's Newton's second law. So what we need to figure out is what is the rotational version of Newton's second law. I figure it's going to be the sum of the torques equals some stuff, but what that stuff is not yet obvious. So that's what we're going to figure out right now is what do I put over here? What do I get when all the torques don't add up to 0? What does it have to equal? Now, to make that work, I'm going to set this aside, and we're going to play around with kind of like the simplest possible test case for a rotational object. And the way we're going to do it is I'm going to imagine that I've got a little speck, a little tiny point of mass m. And what I'm going to do to this little speck is I'm going to put it on the end of like a super thin, super light stick. So thin and so light that I'm going to completely ignore the weight of all this. We're going to pretend like it's massless, right? And then what I'm going to do is I'm going to hammer this end of the stick down to a pivot so that this entire apparatus can pivot freely back and forth around this point. So far, so good? Hang on, my dog is losing his freaking mind over here. Maxwell, come here. Leave mommy alone. Sorry about that. So what's going to happen is I want to subject this piece of mass to a force. And I'm going to go ahead and push it right out here where the mass is. I'm going to push it with a force perpendicular to the stick. And so what's going to happen is this force is going to cause the mass to accelerate. And because the stick is holding it in a particular distance from the pivot, it's going to end up moving along some sort of radius of curvature. Now, we've done problems with things rotating around a pivot before, back in chapter 6. And in chapter 6, what we learned was in order for this thing to move in a sort of circular arc, there has to be a centripetal force, a force directed towards the center and giving it a centripetal acceleration of v squared over r. And in fact, that's what's going to happen here. There's going to be like a tension in this stick. And I'm just going to write off to the side because it's not important right now. But that tension is going to pull it towards the center. And we know that T is going to equal ma in the radial direction. So back in chapter 6, we would have done something like this. Because in order for this thing to move in a curve, there'd have to be a force delivered by the stick of some amount. But what we didn't do back in chapter 6 is we never had a force directed radially like this. Back in chapter 6, all the motion in circles had to happen at constant speeds. But what's going to happen here is that this force is going to cause this mass to accelerate. There's going to be another direction that we're going to have to consider. Now, I saw a hand raise. Amber, what's your question?
Is that T for torque or?
No, this is T for tension. This is back in chapter 6, we saw this. Torque will be a scripty T. So what's going to happen is if we still think about this in terms of like a chapter 4 type question, we would take our forces, do our free body diagram, break them into X and Y components. And in what I have here is the X direction, I'd have this. But what we care about is what's happening in the Y direction. And in the Y direction, I got one force. That's the force that I'm pushing it with. And that should equal the mass of the object times however much it accelerates in this direction. And since this is the acceleration tangent to the circle, we're going to call this AT for tangential acceleration, as opposed to this, which is AC, the centripetal acceleration. So this is the new thing that we're dealing with in chapter 10. We're going to allow AT to not be 0. Now, unfortunately, as we saw last time, talking about this sort of rotational motion with linear variables like A and V and X sucks, right? It's not very well it's not well formulated to refer to variables in that fashion. And so what we'd like to do is to replace stuff we have here with angular equivalents. And we already know some of those angular equivalents. The angular equivalent of force is torque. However, since torque is R cross F, which itself is R times F times the sine of theta, I need to somehow replace F with this. Now, the thing that I notice here is that R is a vector that points from the pivot to my mass. So R is this guy right here. And I notice that in this setup, R and F are perpendicular, which means the angle here is 90, and the sine of 90 is conveniently just 1. So if I want to replace F with torque, all I need to have is, instead of having F, I need to have R times F. And that's easy to pull off. All I got to do is take this equation, and if I multiply both sides of that equation by R, it's still true. So here I'm going to have, I'll multiply this by R times R, I'll have R times F, but I got to multiply this side times R also. So I'll have M times A tangential times R. So all I did here was multiply this equation on the same, by the same, on both sides by the same thing. And this, I can replace with the torque that I'm applying with that force. Now, I got some more work to do over here because here I have the tangential acceleration, but I'd like to replace the tangential acceleration with the rotational equivalent of tangential acceleration. And what I remember from Friday's class was that the linear variable is always equal to the angular variable times r. Aha. So now I can replace AT with alpha, the angular acceleration, times r. Now, if I do that, I'm going to pick up another factor of r. And so what this is going to become is I'm going to have m. This r is going to get multiplied by that r. So it's going to be r squared times alpha. And when I get here, what I notice is that I have an expression that's kind of like F equals ma, because torque is like the rotational version of force, and alpha is like the rotational version of acceleration. But notice, instead of having it be something times ma, it's multiplied by not just m, but mr squared. So this expression here is kind of like the rotational analogy to your mass. It's a thing that determines how much an object resists being rotated. If mr squared is a big quantity, it's difficult to make an object spin. If mr squared is a small quantity, it's super easy to make it spin. So this is going to be like, it's going to play the same role in our torque equations that mass played in our linear equations. We're going to give this a name. We're going to call it the rotational inertia. I. So what's going to happen is when it comes to how hard something is to accelerate, the resistance to acceleration is given by mass, which is measured in kilograms. But when it comes to rotating an object, it's going to matter not just what the mass is, but it's also going to matter how far that mass is from the axis of rotation. If you have mass far away from the axis of rotation, it's going to be harder to rotate than it would be if the mass were close to the axis of rotation. So it's more complicated with rotations. And this mr squared expression is going to be the moment of inertia, or the rotational inertia of a point mass. Now we'll talk in a second about what happens if I don't have a point mass. The answer is it'll be complicated. But for the time being, we have our next set of rotational analogs to our traditional translational motion. We know that we could write the torque as being I, the rotational inertia, times alpha. So for translational motion, we have mass in kilograms, but the rotational equivalent is I, which is going to be in kilogram meters squared as our units of choice. It's not an equal, it's an arrow. So those are our two equivalents. And this is the rotational version of Newton's second law. Now, we'll come back and play with this a little bit in a second, but I want to go ahead and have this out and run down some of the additional rotational equivalents to kind of complete the set here. And what's going to happen is it's going to be super easy now that we know what the rotational inertia is. So for instance, back in chapter 7, we introduced the concept of kinetic energy. Now, if I have an object that's moving left, right, up, down, forwards, or backwards, if it's moving in a straight line, I can write its kinetic energy, K, as being 1/2 m times v squared. But imagine I have an object, and that object is spinning. Now, what's going to happen is, if this object is spinning, it means that every point on this object has a certain velocity as it moves in a circle. It's going to take energy just to make that object spin. So even if it's not moving left, right, up, down translationally, just rotating means you have to have some amount of kinetic energy. It's a rotational kinetic energy. And if I want to write an expression for that, it's super easy to do, because all I'm going to do is take the translational version of that expression and swap it out for the rotational equivalence. So the rotational kinetic energy is going to be 1/2 times not the mass, but the rotational version of mass, I, times not the velocity, but the rotational version of velocity, the angular velocity omega, squared. Super easy. Now, in chapter 8, we learned about momentum, right? Momentum was defined as the mass of an object times its velocity. But this is the linear momentum, the momentum of an object traveling forwards, backwards, left, right, up, down. If I have an object that's rotating, however, we have a rotational equivalent to linear momentum, and that's going to be called angular momentum. And I'm writing it out like this because when we chose to name angular momentum, the letter we chose was kind of weird. For historical reasons, angular momentum is L. Why is angular momentum L? I don't know. Why is radial momentum P? We just pick weird letters. Deal with it. However, all we're going to do is use the same expression. I'm going to replace M with I and V with omega. And in fact, what will happen in chapter 10 is you'll be able to solve angular momentum conservation problems where L is the same before and after in some process. So everything we've seen before, we have a rotational equivalent to it. Super easy. We can do this in our sleep. Any questions about that? Does this make sense? Amber, I see your hand is waved or raised.
I didn't mean to.
Okay. It may have been raised from before. So that's what we've got. That's basically the gist of chapter 10, is that everything we've seen in previous chapters has angular equivalence. Again, from last time we had x for position, theta for angular position. We had v for velocity, omega for angular velocity, a for acceleration, and alpha for angular acceleration. But everything we knew from a previous chapter has a rotational version that we can then play with. Now, here's where stuff gets weird. We've got this rotational inertia, and the expression that we used for the rotational inertia a second ago was mr squared. But that only works if I've got a little speck of mass that's rotating around in some kind of circle. So this works for a point mass, but what it doesn't work for is anything more complicated than a point mass. So what if I have an object that's not a little speck of mass? What if the mass of my object is spread over some region of space? How would I find the moment of inertia for that? And that, it turns out, is a complex problem. But in general, what's going to happen is if you have an object, the more mass that you have that is far away from the axis of rotation, the bigger the moment of inertia is going to be. So if this is my pen here, and I'm spinning my pen around through in some sort of way, imagine that this is my axis right here. I'm spinning it around the center. What's going to happen is there's going to be some section of the pen, a little piece of mass right here that's kind of like a point mass, and it is going to be at a distance of this much from the axis. Meanwhile, on the other end, here's another piece of mass that is a similar distance from the axis. Now, there's also a piece of pen right here. This piece of the pen is a closer distance to the axis. This piece of the pen is going to have a smaller moment of inertia than the end of the pen. And if I wanted to find the total moment of inertia, the total rotational inertia of this entire object, what I could imagine doing is breaking this pen down into a bunch of infinitely tiny little pieces. Imagine it's a bunch of little tiny specks, all of them at varying distances away from that axis. If I could take the mass of this tiny little speck times this r squared, plus the mass of this tiny little speck times this r squared, plus the mass of this speck times this r squared, if I could do that same process all the way down the pen and add them all up, I would get the total rotational inertia for the pen around that axis. Now, what I'm describing there is a calculus problem. We're not going to do calculus problems. I'm just going to have to do the calculus myself and tell you the answer. Turns out, if I did this calculus problem and I spun it around a point in the center, this is my long, thin stick rotating around an axis here in the center, and I do the calculus problem to figure out what the rotational inertia is of this stick, what I find is that I get an expression of 1/12 times the mass of the stick times the length of the stick squared. Neat. Notice the units of the moment of inertia are the same for a point mass or for some funky other shape. For a point mass, the units was kilograms times some kind of distance squared. And that's always going to be true. It's always going to be mass times some kind of distance squared. In this case, it's a mass times some kind of distance squared, but then I got this funky geometric factor with no units up front. And that's going to come from whatever the calculus tells me. Now, unfortunately, that's not the only way I could spin my pen. I could, instead of having the pen pivot around the center, I could have it pivot around one end. Now, you'll notice that if I pivot around one end, there's going to be some piece of the pen that is half a stick away, just like there was before when I had the axis in the middle. There's some piece of the pen that's half a stick away, just like before. However, now when I'm pivoting around this end, this far end of the stick is now twice as far away from the axis as anything was in the previous example. And so when I add up all the mr squareds, when I rotate it around the end, I'm going to get a different expression. That's nuts. It means the rotational inertia of an object doesn't just depend on the size and shape of the object or on the mass of the object. It also is going to depend on how you choose to rotate it. It will be easier to rotate it in some ways and harder to rotate it in other ways. So if I'm doing the same stick, but I put the axis at the end, and I break all these down into little tiny point masses, and I add them all up with some calculus, I get a moment of inertia that's a different expression. Spinning it around one end is 1/3 the times the mass of the stick times the length of the stick squared. Notice 1/3 is 4 times bigger than 1/12. It is 4 times more difficult to rotate the stick in this fashion than it is to rotate the stick here in the center. Usually when we're in class, what I'll do is I'll grab, like one of the big meter sticks that we have in the classroom. And if you grab it in the middle and kind of wiggle it back and forth and rotate it, you can feel how much resistance you get to rotating that object. Now, if you take that same object and you grab it at the end and you try to rotate it back and forth at the same rate, you'll find it's considerably harder because it's as if the mass of the stick got way longer. So try this at home with different things. Like here I've got a book. And the expression for the moment of inertia of this book is going to depend on how I rotate it. So if I rotate it this way around the center, then here's my axis, put it on this side, and the furthest anything ever gets from the axis is half a book length away. And so I face a certain amount of resistance when I rotate it this way. However, when I rotate it around the end, it's much more difficult for me to handle because now I've just made the axis over here and I've got some of the book that's twice as far away. So it's harder to spin the book this way than it is to spin it around an axis through the center. So any shape you can imagine, you're going to have the same sort of behavior. Now, if you look in chapter 9, or excuse me, in chapter 10, there is a chart in chapter 10 where they figure out the different moments of inertia for all kinds of different shapes. And, you know, I'm not going to require that you memorize any of these formulas. You know, I have to figure them out myself. But you should at least be familiar with what those different changes are. So for instance, imagine I have a sphere, like a round ball, and I'm rotating that round ball around an axis in the center. Well, it turns out that the moment of inertia you get for that is, I believe, 2/5 times m times the radius of the thing squared. So that's for a sphere. Imagine that you've got a thin kind of hula hoop shape where all the mass is concentrated right here at the outside edge, and you're rotating it around the center. The moment of inertia for that is 1/2 mr squared. If I had instead a solid disk, like a plate or something, a solid flat disk, oops, I'm bad, hello. The hoop is mr squared. The disk is 1/2 mr squared. To see why that is, for the hoop, every little piece all the way around is always the same distance from the center. So when I take mr squared for this, plus mr squared for this, plus mr squared for this, it ends up just adding up to the total of all the masses, m, and they all had the same r. So that's pretty easy why the hoop has the same expression as the point mass. But for a disk, what's going to happen is for every piece that's way out here at the outside edge, there's another piece that's very, very close to the center. And this piece here is easier to spin than this piece out here. And so when you add them up, you end up with less than it took to spin the hoop. Wow. Back when I was a kid, I used to have a lot of these toy cars. And there were some of these cars where you could put them on the floor, you could pull them backwards, and it would wind up some mechanism inside the car. And when you let them go, they go shooting forward. That was all the rage when I was a kid in the late 70s and early 80s. But some of the toy cars that I had were different. And for these, what you would do is instead of taking the car and putting it on the floor and dragging it backwards and winding something up, instead what you would do is you put them on the floor and you push them and rev them against the floor very, very rapidly. And what would happen is, I always thought these cars were like broken or something, because the wheels were super, super stiff. It was super, super hard to get those wheels rotating. But the cool part was that if you rev them on the floor and you push against those really tough to rotate wheels several times, they'd get to moving. And then if you just kind of set it on the floor and let it go, those wheels would want to keep turning and the car would skitter across the floor away from you, right? So it was like, it was really hard to rev the wheels up, but once they got revved up, they didn't want to stop. And of course, being an inquisitive kid who wanted to know how his toys worked, of course I took them apart, right? I took those cars and dismantled the heck out of them. And when I took that car apart, what I saw was that on the inside of the car, it had kind of connected through a complicated set of gears, this little round thing inside the car. And that round thing had like a metal band, a thick metal band that ran around in a circle, kind of suspended on this plastic gear. So what that thing was a hoop, right? It was like having a little metal, super heavy metal hoop inside there. And every time I revved those wheels forward, what it was doing is it was making that hoop start to spin. And what happens is, because it's a hoop, it has a rotational inertia of mr squared. It's pretty big. it takes a lot of torque to get that little hoop inside it. They call it a flywheel, to get that flywheel rotating. But because it has a large rotational inertia, if it takes a lot of torque to make it accelerate, it also takes a lot of torque to slow it down. And that's why once you got the wheels going, they didn't want to stop. And you could exploit that by letting the thing zing forward and away. Neat. So check out the chart in chapter 9. You'll see all kinds of groovy rotational inertia formulas for different sorts of shapes. And you're always going to want to choose whichever one is appropriate to the problem that you're solving. So let's put all this garbage together. Let's solve a problem that involves a rotational inertia. So imagine, let's start with something simple. I've got a seesaw. And what's going to happen is I've got a pivot in the center of the seesaw. The seesaw itself is, let's say, 2 meters long. And what I'm going to have happen is I'm going to have 2 kids sit on opposite sides of the seesaw and generate some torque. So let's imagine the kid I have sitting on this side is going to push the seesaw down with a force of, let's say, 500 newtons. Meanwhile, on the other side of the seesaw, the other kid is smaller. He's going to generate 300 newtons of force, also pulling the seesaw down. And what I would like to determine is what is the angular acceleration of the seesaw in this scenario. Well, it's pretty easy to figure out because what we have is the rotational equivalent of Newton's second law. We know that the sum of the torques is equal to I times alpha. I should probably specify a mass for this thing. Let's say that the seesaw has a mass of, let's say, 10 kilograms. So when I do this, first, I need to figure out where the axis is, and I know that the seesaw is going to pivot right here around the center. So on the right-hand side, I'm going to have to know what I is, but I know that for a long, thin rod rotating around the center, I know that the expression for I is going to be 1/2 times the mass of the seesaw times L squared. So I'll use that for I. And I'm solving for the angular acceleration, so alpha is what I want. So heck, the right-hand side is easy. I'm going to put in 1/12 ml squared times alpha. Now on the left-hand side, I need to figure out the sum of the torques. And I've only got 3 forces acting on this seesaw. I've got this kid pulling down, this kid pulling down, actually 4 forces, because gravity pulls on the seesaw, but it's going to pull at the center of mass, which is, I'll call that mg. There's also going to be a normal force from the pivot that's going to push upward. And if I was interested at all in what that normal force was, I could certainly solve for it, but the question doesn't ask, and I don't especially care. And when I'm calculating torque, the torque is RF sine theta, and R is the distance between the axis and that force. And of these 4 forces, 2 of them are right here at the axis. They're going to have an R of 0. So these 2 forces here, they're not going to generate any torque. I'm not going to care about them at all. Meanwhile, I am going to get a torque from this force, and I am going to torque from this force. So I'm going to have to calculate those. So in this problem, when I do this torque, this torque is going to make the thing want to rotate in a counterclockwise direction. Traditionally, counterclockwise is the positive direction, so let's go with that. So that's a positive torque. So the torque from this is going to be R for the 300, which is this distance, which is half of 2 meters or 1 meter. So it's 1 meter times 300 newtons. And it's positive. It's going to be times the sine of the angle between F, which is straight down, and R, which is straight across. But that's 90 degrees, and the sine of 90 is conveniently 1. So I got 300 Newton meters of torque generated by this kid over here. Meanwhile, over here on this side, this torque makes it want to rotate clockwise, which is the negative direction, so minus, and it's going to be the R for this guy, which is 1 meter, times the F for that guy, 500 newtons. Yay, super easy. And so what's going to happen is when I solve for alpha, I'm going to have 300 minus 500 is negative 200. Then I'm going to divide by 1/12 times m. We said m was 10. And L was 2 squared. So when I go in to calculate alpha, that's what we're going to get. So 200 times 12 divided by 40. So I get that alpha is equal to 60 radians per second squared. Super easy.
How'd you get your L again?
I looked at the picture and said that the length of the thing was 2 meters. It was given in the problem. So, what would change if I were to take the heavier kid and have him inch halfway up the seesaw? What if instead of sitting out here, he were to sit there instead? What would change? This was, by the way, negative. So in this case here, the negative tells me it's going to go in the negative direction. So the big kid sitting here and the small kid sitting here is going to rotate in a clockwise direction at 60 radians per second. If I move him here, however, what's going to happen is the torque from this kid is the same as it used to be. But the torque from this kid is smaller now because even though the force is the same, I'm replacing it with an R, which is no longer 1 meter, it's half a meter. But now what's going to happen is 0.5 times 500 is 250. All of a sudden, this is not negative 200 anymore. It's positive 50. And so now what's going to happen is I'm going to end up with not negative 60, but when I do it this way, it'll be positive 15 radians per second squared. So notice this kid inching up here has caused the teeter-totter to balance and rotate the other direction. But all we had to do was Newton's second law for rotation, fill in whatever we knew, and solve for whatever was missing. Super easy. We can do this in our sleep. Any questions about that? You guys feel pretty confident there? Let's do something more interesting. Let's do energy conservation. This is perhaps germane since you guys have an exam going live later today in which you're going to be forced to solve energy conservation problems. So in a way, this problem is going to be almost a kind of review. So if I had asked you, hey, here's a funky, weird shaped slide, and I put an object at the top at a height of, let's say, 10 meters, and I ask you to figure out how fast is this object going to be going at the bottom of the slide, assuming that it slides frictionlessly the entire way down, you should be able to solve that problem using energy conservation, right? That's a chapter 7 problem. How would I do it? Well, since there's no non-conservative forces, I can say that the initial kinetic energy plus the initial potential energy should equal the final kinetic energy plus the final potential energy. And we've done this problem before, so I'm going to go through it quickly. If I start this thing off at rest, that's conveniently 0. But the potential energy it's going to start off with is going to be the gravitational potential energy, mgh initial. Now, at the bottom of the slide, it's going to have some kind of speed, so k final is not going to be 0 anymore. It'll be 1/2 mv squared. And u final is going to be mgh, but down here it's at a height of 0, so h is 0, that takes that whole thing away. So what am I solving? I'm solving this, and I want to find v. Notice the mass of the thing cancels out, and when I solve for v, I'll multiply by 2. I'll get 2gh initial square rooted is equal to v. And this one's pretty easy to do in your head. 2 times 9.8 is 19.6, times 10 is 196, and 196 is a perfect square. It's traveling 14 meters per second when it gets to the bottom of that hill. Yay! Super easy. Let's make it more complicated. Because what I'm going to do is I'm going to take 2 other objects. I'm going to put them at the top of that hill, just like that. Except these 2 objects are going to be, how about a solid hoop? So a thin hoop, a solid disc. Excuse me. And why not? Let's put a sphere up here. And these objects aren't going to slide. Allergies, Jesus. They're not going to slide to the bottom of the hill the way this box did. Instead of sliding, they're going to roll. They're going to roll down that hill without slipping. Now, if they're going to roll without slipping, when they get to the bottom, do I expect that they're going to be going faster or slower than 14 meters per second? Or will it be the same? What do you think?
Faster.
Convince me. Why do you say faster?
Maybe because it's gonna have the speed of it rolling and the speed of it going down.
Okay, well, that's certainly true that the fact that it's rolling is going to make a difference. And if you think about this in terms of energy conservation, you can figure out the answer based on that. Because energy is going to be conserved for each of these guys as well. So what's going to happen is K initial plus U initial should equal K final plus U final, just like before. And other things are going to be very similar. For instance, when these things, all of them get to the bottom of the hill, U final is going to be 0. So I can make that be 0, just like before. And I'm going to have these guys starting out at rest, which means they're not going to be moving at first, nor are they going to be spinning at first. So the kinetic energy, that's 0 too. The potential energy, same as before, mgh initial. So far, everything looks exactly the same as what we had before, except for one thing. Amber, you had a question.
Well, will it lose energy because it's rolling?
Well, what's going to happen is when we're doing the final kinetic energy, before we only had one kind of kinetic energy. It was sliding, but it wasn't rolling. So it had translational kinetic energy, but it did not have rotational kinetic energy. But each of these things, they're going to be moving sideways. So they're going to have translational kinetic energy, 1/2 mv squared. But in addition to that, they're going to be spinning as well. So all I have to do is K final is going to have 2 parts now. It's going to have the translational part, plus I got to add a rotational part. So you can see that I had this expression before, I have this expression now. Do we want to revise our answers? Do we still think it's going faster? I don't know, Tom. I'm checking my phone. I don't know. Okay, we'll think it through this way. In the original problem, we started off with a certain amount of potential energy. Let's imagine, for the sake of argument, that MGH was 100, right? Now, in the original problem, if I started off with 100 joules of potential energy, at the bottom of the hill, I had 100 joules of kinetic energy making me go sideways really, really fast. But what about these guys over here? They're all starting out at the top here. They've got 100 joules of potential energy, just like the other guy did. However, they're taking that 100 joules that they started with, and they got to split it two ways. Some of that 100 joules has to go into the translational kinetic energy, and some of that 100 joules has to go into just making it spin. So if it takes 25 joules to make it spin, they're only left with 75 joules for making it go fast. And 75 joules of kinetic energy means I'd be going slower than if I had all 100 as kinetic energy. All three of these objects are going to end up traveling slower than 14 meters per second because they've got to use some of their energy just to be spinning. So contrary to like your intuition, they're not going to go faster because they're rolling. They're actually going to end up going slower because they've got to reserve some of the energy in order to make themselves rotate. So real quick, let's see if we can't solve this problem. All right. Now, let's do the easy one first. Let's do the hoop. Now, what's going to happen is for the hoop, I is going to be m times r squared. And so what I can do is I can replace I with that. So I've got mgh initial equals 1/2 mv squared plus 1/2 mr squared times omega squared. And you'll notice that when I do that, the mass of the hoop cancels out, which it canceled out up here too. It doesn't matter what the mass of that hoop is. Now, when I go to solve for v, though, I still got to get omega. And omega is the angular velocity that the thing's spinning with. However, if I have a wheel and it's rolling, the faster the wheel spins, the bigger omega is, the faster the wheel moves sideways, right? The rate of translational motion ought to be related to the rate of rotational motion. That's how your speedometer in your car knows how fast you're going. And what's that relationship? Well, we know from last time that v is equal to omega times r. So what I'm going to do is I'm going to replace omega with v over r.
We're doing the disc right now, right?
We're doing the hoop. I assumed it was the hoop when I used mr squared rather than 1/2 mr squared or 2/5 mr squared or something else. But look what's going to happen. When I plug in this, I'm going to have gh initial equals 1/2 v squared plus, oops, that's 1/2 r squared v squared over r squared. Oh, look, the radius of the hoop's going to cancel as well. So I end up with 1/2 v squared plus 1/2 v squared. That's equal to v squared gh, which means that the velocity I get is going to be the square root of g times h initial. And it's pretty obvious that gh initial is going to be smaller than 2gh initial. That's going to be the square root of 98, which is about 9.9 as I recall. Yeah, about 9.89. So, as expected, this hoop ends up traveling slower than the sliding box. Now, we don't have time to do the math on the other two, but if I release all three of these guys at the same time, who do I expect to be going the fastest when they get to the bottom? Any ideas?
The box.
Well, obviously the box, but for the three rollers, which of the three rollers is going to be going faster at the bottom? Remember, a disc has a moment of inertia 1/2 mr squared, and the sphere had a moment of inertia of 2/5 mr squared. Whereas
So the hoop's
going to be going the fastest. It's backwards. The hoop's going to end up going the slowest of the three because mr squared is bigger than both of these. And of the three of them, 2/5 is slightly smaller than 1/2. So that means that it has the smallest rotational inertia. It's the easiest of the three to make spin, and therefore it's going to have the smallest amount of energy used for the spinny part. And this will be traveling slightly faster than either of the other two. The disc will come in second place, and the hoop is going to be the slowest of all of them because it has the largest rotational inertia, and it's going to have to consume the most amount of its total energy just to make it spin. All right, that's all the time we have for today. I will see you guys on Wednesday. Be on the lookout for the exam posting sometime this evening. Once it goes live, you'll have 48 hours in which to turn it in. Make sure that you set aside a 2-hour block because once you start it, it's going to close once you finish. There is a clock that's going to be ticking in 2 hours. So don't start it unless you know you've got 2 hours to spare.
Wait, it's 48 hours?
48 hours. 2 days. So it will be due sometime on Wednesday. Probably midnight on Wednesday. Maybe it's slightly more than 48 hours, but that's my goal. Got it? All right. Have a good day.